In this third capsule on carbocation rearrangements, we look at a new way carbocations rearrange, and that is here, reaction number 3. So, the first two reactions we have seen in the previous capsules. The very first one, you will see that in carbocation rearrangements 1, it focused on this reaction between these two compounds. This is the expected product, and then there is an unexpected product, and we looked at why that unexpected product formed and how that unexpected product formed, and that involved a rearrangement of the initially formed carbocation. So the initially formed carbocation in this one, again just to refresh ourselves, is this. That's a carbocation that forms initially as an intermediate. That carbocation is secondary carbocation. It rearranges to this particular carbocation, which is a tertiary carbocation. So, and the tertiary carbocation undergoes a 1,2 hydride shift, and then the secondary carbocation undergoes a 1,2 hydride shift to form a tertiary carbocation, which then combines with the bromide ion to give the product. Okay. So I just highlighted the hydrogen in red. The hydrogen in red, that is the hydride that shifted from that carbon to this carbon to give this product. Now, in the next video, carbocation rearrangements 2, we have looked at a very similar compound, but the difference is here you have a CH3 instead of a hydrogen. So in this reaction, the methyl group shifted with 2 electrons, so it is called a 1,2 methyl shift. Again, you had this initial carbocation. In the second case, that initial carbocation will be this, and then the rearranged carbocation will be that. So what you noticed in reactions 1 and 2, the carbocation that forms in the first step of the mechanism, the secondary carbocation, is rearranged to the more stable tertiary carbocation. Now, let's take a look at reaction 3. Reaction 3 also involves a reaction between a double bond, an alkene. Alkenes are compounds with one double bond. So, see a reaction between the alkene and HBr. This is the expected product, and then you see the unexpected product. This is the unexpected product. You notice that the 4-carbon ring became a 5-carbon ring. So, we call that a ring expansion. Now, why did that happen? And how did that happen? So let's take a look at the mechanism. The mechanism is pretty similar. This is the good thing about organic chemistry. We just learn the fundamentals, and then we can apply those fundamentals to new reactions. So alkene, the double bond, electrons pick up the proton from HBr, resulting in a carbocation. So this is the step 1 of the mechanism, where the alkene, this is how we show the Calderos electron movement, which results in this particular carbocation plus bromide ion. The reaction, so these are the products of step 1 of the mechanism. This is step 1. So we show this, we show the double bond electrons moving to H plus of HBr, HBr bond breaking, which gives us this particular, and also you will notice it is a CH2 right now in the alkene. The CH2 carbon picked up the H plus, became CH3, so here it's CH3. So these are the products of step 1. This is the intermediate, it's not the final product. The intermediate here, just to emphasize it, it's a tertiary carbocation. As you see, this carbon is connected to 3 other carbons, 1, 2, 3. So these are the products of step 1. And in step 2, the reaction between the carbocation carbon and then the bromide will give rise to the expected product. Now, that's fine. How are we getting the unexpected product? That's what we want to work on. Okay, so this is the intermediate carbocation that forms. So let's look at it. It's a tertiary carbocation, and if we compare it with the reactions that we looked at in the previous couple of capsules, the cations, the intermediate carbocation that formed is a secondary carbocation, which rearranged, there's a hydrogen there, that hydride moved there, so which rearrangement led to a tertiary carbocation. That sort of made sense because tertiary carbocations are more stable than secondary ones. Here though, we have a tertiary carbocation. In this case, in reaction 3, we have a tertiary carbocation, and why is that moving? Why is a rearrangement? Why did a rearrangement happen here? So let's take a look about that. Why? So the why is dependent on the other part of the molecule. So there's the carbocation, all right, it's stable, all right, tertiary carbocation. Now, this part of the molecule though, if you take a look at that, the cyclobutane ring, that is, we call that ring, we say it has something called an angle strain, quite a bit. There's other strain too, but let's focus on angle strain right now. So there is all these carbons, 4 carbons of the cyclobutane ring are all sp3 hybridized. And we know sp3 hybridized carbon, the ideal, wants a tetrahedral shape and 109 degrees, roughly bond angle. So given with that information, which we know, from straight chain compounds like that, which are perfectly tetrahedral, have this nice ideal bond angles, but we are taking that sp3 carbon, and when this cyclobutane ring forms, the ideal bond angle, close to 109 degrees, is sort of restricted to. So if you just think this as a square type of compound, really, but take that, the approximate bond angle here will be like 90 degrees. So we are forcing the sp3 carbon, which an ideal bond angle is like 109, to adopt a very restricted 90-degree bond angle. So which introduces the angle strain. So keep that in mind. So that makes the compound unstable, the cyclobutane ring unstable and prone to rearrangement if possible. So you see this carbocation here, this part of the molecule is somewhat unstable because of the inherent angle strain, and that is why the cyclobutane ring expands to cyclopentane ring, and we'll see that shortly. So let me redraw this and number them so we can see that somewhat clearly. So I'm starting with the carbocation carbon, and I'll just number all these carbons. 1, 2, 3, 4, 5, 6. Now, we know that the ring expanded because we see that it's given to us, that's formed, and we are trying to explain that. So we know it formed. We are not trying to explain how that formed. So this bond, the 3,6 carbon bond, breaks up. Then cyclobutane has to make cyclopentane, right? So cyclobutane needs to open up. So the 3,6 bond is the closest bond there, or you can think about 3,4 bond, but easier to show this way. So this way, the 3,6 bond opened up, and 6 now binds with carbon 2. This is similar to the 1,2 methyl shift we talked about in the previous video. Here, instead of methyl group, an alkyl group is moving, the CH2 in this move. So what do you get? Let's redraw this, the product. So I have carbon 1 there, carbon 2, that methyl group is there. Carbon 2 is connected to carbon 3, 4, 5, is connected to 2. So you get the expanded cyclopentane ring. Now, since this carbon 6 took both electrons, 3,6 bond is formed by sharing one electron from carbon 3, one electron from carbon 6. Carbon 6 took both electrons and formed the bond with carbon 2. So carbon 3 has a positive charge. So that's how we are getting a secondary carbo. Notice this is a secondary carbocation. So you may ask, why is a tertiary carbocation becoming a secondary carbocation? That's opposite to the stability order. We know that tertiary carbocations are more stable than secondary. So this way, which we have seen in the previous 2 videos, makes sense. But why is this happening this way in this particular compound? That is because of the relief in angle strain. So angle strain that exists in a cyclobutane ring, that is relieved. That by opening up to a 5-carbon ring, that angle strain is removed. So you get this secondary carbocation, then Br minus reacts there, and then you get the product, unexpected ring expanded product. Now, so this is the third type of carbocation rearrangements we see normally. So whenever you see problems like this, make sure you number the carbons so you can easily identify, keep the bonds together. So numbering makes it easier to follow which bond is breaking, which bond is forming. So with that said, we have talked about 1,2 hydride shift, 1,2 method shift, and now we have a ring expansion. 3 types of carbocation rearrangements. So in the next video, we'll talk about the stability of cycloalkanes. So we have compounds, starting from cyclopropane, cyclobutane, cyclopentane, cyclohexane, so on. So we'll look at which one of this is more stable, which is the least stable, and how do we determine that experimentally. You can look at some numbers and make sense of those. Stop now.